So welcome to the last lecture of the semester. For this one, we're going to talk about the double shear test. So in this experiment, what we would have done is we would take 3 rods. We would take aluminum 606 T6, copper, and then 1018 steel. And I have green, red, and blue, where each rod is basically color-coded for that respective color. So in the lab, you can know which one was which. And then what we're going to do is we're going to use the MTS machine, and we're going to have shear failure for each of these rods, but in this case we're going to have a double shear failure instead of single shear, and we'll talk about that a bit later on. And then what we would do is we would run this test 2 times for each specimen. And then in the report you're going to compare the experimental shear strength versus the theoretical shear strength, and then we'll kind of, discuss the accuracy of the theoretical versus experimental results. And then we're also going to look at the bearing stress that we have for each rod, so hopefully you remember that from your 331 class. And then the last thing we're going to do in the report is graph the shear stress versus the crosshead position for each specimen, and then we'll compare them. There actually should be one more thing. We're going to have pictures at fracture for each of these specimens, and then you'll kind of comment on that fracture appearance, so similar to what you did in Lab 5. Okay, so we're going to talk about some of that basic theory first, and then I'll show you the interactive procedure from VKS so you can get an idea of what we would have done in the experiment. Okay, so shear stress, it's going to be defined as the intensity of the internal force that acts on a surface parallel to the internal force. So if we think back to our first lab, we had normal stress in the scenario of tension. So that's here on the right. Okay, that's right here. So in this case, we had the force being perpendicular to our surface. Now in the case for this lab, we're going to have shear stress, and that's going to be a force that's parallel to the surface of the rod. So if I have a force here, F, right there, and I apply this force, it's going to fracture this rod that I drew, and this fracture surface is going to appear in pink, so right in here. Okay, so in this case we have shear stress again, and it's going to be called single shear because we only have one fracture surface. For our experiment, we're doing double shear, so I kind of drew a little schematic here. So it's going to look something like this in the lab, and I'll show you the actual picture in just a moment. But what we have is 2 supports on the end of the rod, or towards the end of the rod. Okay, there, and then we're going to have, it's not really a block, you'll see later on, but we have some object here that I'm representing as a square, and we're going to apply a force down on our rod there, and that's going to result in shear failure. But in this case, we're going to have double shear, because we're going to have 2 different fracture surfaces for A1 and A2. Okay. So, to find shear stress, typically, if we have a single shear, what we would have is tau equals V over AV. So V, that's going to be the shear force, and then AV, that's going to be the area that's exposed after this shear stress fracture. Okay, so for the case of double shear, we have 2 surfaces, so all we have to do is put in a 2 right before the area. Okay, so for this, all we have is tau, the shear stress, is going to be equal to V, the shear force, divided by 2 times A sub V, where A sub V is the exposed shear area as mentioned before. Okay, so really simple stuff. There's really not much theory to go over here because it's so simple. It's just this equation. and we're going to go ahead and use that, okay? Okay, so now we'll first talk about the experimental shear strength and then the theoretical shear strength, okay? Okay, so the experimental shear strength, this is basically the formula that we have written above. So this is going to be just tau experimental equals F max, that I could say V max, doesn't really matter, just some load, divided by 2 times the cross-sectional area, which is a circular rod. So F max, that's going to be the maximum load that we have recorded from the MTS machine at fracture. So obviously we just want to make sure we have the load at fracture for the shear. Okay, so for the theoretical shear strength, this is basically just from an empirical formula that was kind of found that matches up well with the experimental values that we get for the shear strength. So for all of the metals, it's just going to be tau max, or tau theoretical, is equal to 65% of the ultimate tensile strength. So we're going to use that for each metal that we have. Okay, so this isn't going to be, perfect kind of relationship here, obviously, and in addition to this, we have different forms of stress, like bearing stress and bending stress, that are going to occur in this experiment. So it won't be just shear stress, but despite that, we're going to use this formula, and then we'll compare this value to the experimental value. Okay, so the other thing that we're going to measure in this lab is the bearing stress that we're going to have on each of these rods. So if you remember from 331, the bearing stress is going to be the stress that occurs on the shared area between the rod and, in this case, the hole that it sits in. This will be easier to see once I actually show you a picture, and then you can kind of get a sense of it. So the bearing stress, that's going to be equal to F divided by A sub B. We'll change that to F max. We're also going to use that force that we have at fracture. And then AB, that's going to be the area of contact. So in the case of our lab, that's going to be the length of the rod that's in contact with the surface that it's touching, and then we're going to multiply that by the diameter. So again, another pretty simple formula, and that's all we have to do for this lab. Okay, so now I'll go over the procedures so you can get an idea of what is really going on. Okay, so this is the setup that we have for this experiment. So on this bottom part here, we would have each rod individually. We would put them in through a hole here, and then this top part, this would come down. It would apply a load on the rod, and then it would fracture it. We would have a shear fracture in 2 spots for the double shear. So we have our 3 rods here. We have aluminum 6061 T6, we have copper, and then we have 1018 steel. Okay, you'd have to measure the length and the diameter of each rod. You need to make sure that you measure the length for the portion that's actually being fractured, but you're just going to add the data so you don't have to do that. Okay, and then we have this centerpiece here, so this would go in the middle of this configuration here, and then these 2 end pieces, they would kind of slide in these holes here. So you see we have these 2 end pieces here, then we have the middle portion here, and then you would have the rod going through. It would be threaded through these holes. Okay, so then you see this top portion here, that came down, and then it fractured our specimen. At this point, it's actually not totally fractured. What you would have to do is take the handset controller, and then you would use the thumb wheel here, and you would continue to apply load until the centerpiece actually falls down all the way. And at that point, it would be fully fractured, and you would get that load. Okay, let's see if there's any better pictures here. Okay, that's what it shows right here, just that we need to use the thumb wheel to fully fracture it. Okay, so here the specimen fully broke. In this case, that looks like it was copper. Okay, and then what you do is you would take pictures with this camera. You would have done this on the Sharpie test as well. So you'd get a picture that looks something like this. In this case, it looks like we have either steel or the aluminum. Okay, so you take a picture and then you can kind of see the fracture that we have. So in this case, it looks like we have some ductility, but it seems more brittle. What you would see if you had copper, I went right past it. Okay, so if you had copper, you see this kind of smearing here. This would be over the majority of this surface here because copper is much more ductile than something like steel. So you should have pictures in the provided data as well. And basically you're going to comment on the fracture appearance for each of these metals and kind of explain why they look the way they do. Okay, so what I'm actually going to do now is open up SolidWorks, and I'm going to show you, kind of give you a better idea of this bearing surface that we have, or this bearing stress. Okay, so I'm trying to find a good picture here. Okay, so in this case, you see that we have our specimen loaded in. But to show you this bearing stress, let's pull this up here. Okay, so I have my assembly here for our test setup. It doesn't really look exactly like this, but it's good enough to give you an idea of what is going on in the experiment. So here I have my two end pieces, and then here is the center piece. So if we do a section view, first I'll go to the front plane. Okay, so I'm going to do a section cut here, and we'll do this on the top plane. Okay, so the bearing surface here is going to be this area that's highlighted right here. This is going to be the shared area. You would really take off these end pieces right here, so pretend that the highlighted portion is just all of this right here. So we're taking this length from this point right here to this point over here, and we have all of this area. So we're taking this length, and then we're going to multiply it by the diameter of the rod, and that gives us the shared area. So hopefully that kind of gives you a better idea of what I mean by the shared area for the bearing stress. Okay, so that's it. If you have any questions on this experiment, feel free to let me know. Send me an email, or we could talk about it in Zoom or Discord, whatever you want. And yeah, okay, that's it for this lab, for this lecture. I hope you enjoyed the semester, and hopefully you learned something in each of the lectures and the labs. It sucks that we couldn't do the last 3 labs in person, because I think that's really valuable to actually do the labs. So hopefully you still have an idea of what we are going to do in each lab from all of the interactive procedures that I showed you and some of the videos that I showed as well. Okay, so I hope your semester's going well, and hopefully your finals go well too. So, see you next time.